Okay, everyone, we will speak a little about the stability of a model that's modeled by an ordinary differential equation. Now, going back to using the D operator approach to solving differential equations, you may recall that when we considered the homogeneous type differential equation, in which case the right hand side was 0, the solutions y were a sum of things of this type, where each of the YA, YB, YC had a particular structure, and the structure of these was, so whether it's a YA, YB or YC, these solutions always had the structure that they were some function of t or x, whatever the independent variable was, multiplied by some exponential. Let's suppose it is e to the at. So this one, for example, may be some function of t multiplied by, say, e to the bt, etc. And something with that. And the important thing is that these exponential part of the solutions, remember there were a sum of solutions. Each separate sum had the structure that I'm speaking about here, that you had an exponential multiplied by some function in this bracket. So in each case, you had these exponentials multiplied by that, exponential multiplied by that, etc. And the nature of these exponentials would tell us whether the individual parts, that is, for example, this part, that part, and another part coming from there, etc., would go to 0 or not. So we know that in general, an exponential e to the, say, capital A times t would go to 0 if the capital A is negative. It would not go to 0 if the capital A is 0 or positive. So this was in fact an important condition for the exponential to decay. What that means is, for the solution as a whole, that means this whole solution here of the homogeneous part, for that to go to 0, each individual part, this part, that part, and that part, each individual part, etc., would have to go to 0. For each individual part to go to 0, each of the exponentials that occur in each term, for example, in the first case, you had this e to the small at had to go to 0. E to the bt had to go to 0. E to the ct, etc. All these individual terms would have to have their exponential factors going to 0. It means then that in each of these individual parts, the exponentials would have to be such that this coefficient of t, let me highlight that even more, that little a there has to be negative, this little b here has to be negative, and in each one, the exponential part of the term would be such that this factor, little a, little b, little c, etc., would have to be negative. Otherwise, if any one of them is positive, then one part of the solution will not go to 0, which means the whole thing, the whole function y, the solution will not go to 0. Right. So, where do these little exponents come from? The little a, for example, there, the little b that comes there, the little c that would appear in the next solution, the coefficient of t in the exponential part, where does it come from? you may recall that these little coefficients of t in the factor, in other words, I'm now focusing on that. In the solution of differential equations, especially the homogeneous differential equations, using the d operator method, these coefficients of the exponentials, those come from the roots of the polynomial p of d. So let us look at the differential equation, homogeneous d operator type differential equation, p of d on y equal to 0. You remember that to construct the solution y, we said all we need to do is to identify the roots of the polynomial p of d. So if the polynomial p of d was of order n and it had, suppose, n roots, let's suppose they were all real, just for the first case, then the solution y would be a product, a constant e to the alpha 1t or e to the alpha 1x, depending on which variable you use as your independent variable. And the last one will be an, a constant, e to the alpha nt. That's how we constructed these solutions of the homogeneous differential equation, where the right hand side is 0. So that if any of these alpha i's, alpha 1 right up to alpha n, is positive, this solution y will not decay to 0 as t goes to infinity. All of them have to go to 0 for the solution y to decay to 0. That is, alpha 1, alpha 2, right up to alpha n will have to be negative. That means all the roots of the polynomial p of d will have to be negative for this solution to go to 0 or decay to 0. What happens when these roots were supposedly imaginary, complex? You may recall that if any of these roots was complex, then there was a complex conjugate. In that case, the solution or part of the solution. So let's suppose we had the complex case. So if, say, alpha 1 is complex, then of course there'll be a complex conjugate. Then alpha 2, say, is complex conjugate. You will always get this case. Then there was a solution, then part of the solution looked like, let's call it y star. Y star is part of the solution somewhere in there. Then y star was of the form that involved causes and sines. So let's suppose it is a1 cos x, that's a1 bar, say, cos t plus b1 bar sine t. Let me write that nicely. Right? And it was multiplied by e to the some exponential. And it will be an exponential of the type e to the something t. Incidentally, this coefficient of t there did not be 1. That was the imaginary part of the complex roots. This was the real part of the complex root of alpha 1, alpha 2. So that if this was positive, y star would not go to 0. So the solution y as a whole will not go to 0. So now we can sum up the two together. So in other words, this part there would have to be negative for this whole thing to go to 0 as t goes to infinity. This part here, in fact, is the real part of the complex roots. So we can put together what I've discussed here and what happens in the equivalent complex case up there. To sum it up then, for the stability, here by stability I mean that the solution will decay to zero. For the stability of this differential equation model, all the roots of P of D, or equivalently, all the real parts of the roots of P of D have to be negative. So we can put it all together in all the real parts that will take care of real roots or imaginary roots. All the real parts of the roots of P of D, the roots of P of D have to contain negative parts, have to contain or be negative parts. Forgive the English. So the emphasis here is, I should say, all the roots of the polynomial P of D have to be negative to guarantee the stability of the solution of P of D on y equal to 0. So to test stability, look at the differential equation you're busy with, that's P of D on y equal to 0. Consider the roots of P of D, whether they are complex or real, doesn't matter. The real parts have to all be negative to guarantee stability.